Alright, today we're just going to talk briefly about the imaginary root theorem and the irrational root theorem. Okay? The imaginary root theorem. First of all, we've talked about imaginary numbers or imaginary solutions. Okay? When do imaginary solutions end up happening? When you square root negative numbers, right? When you square root a negative number, your answers always have an I in it, right?
Yes.
Okay? So, we've talked about imaginary solutions. Roots is just another word for solutions or zeros, okay? So we're talking about imaginary zeros, really, is what we're talking about, okay? And we've mentioned this a little bit already. When you get an imaginary zero or imaginary answer, is there only just one or does it always come in pairs? Always comes in pairs, right? Okay? Think about it. When you're doing your quadratic formula, x equals negative b plus or minus the square root, and let's say the number under the square root, is a negative 16 or something, okay? Well, the square root of negative 16 is 4i, right? Square root of negative 16 is 4i. So you get 10 plus 4i divided by this, and 10 minus 4i divided by that. There's always two different answers that are imaginary. They're always going to come in pairs. One's going to be the plus, one's going to be the minus, right? Okay? The imaginary root theorem basically just is saying that imaginary roots or imaginary zeros always come in pairs, and they're always conjugates of each other. You should recall the word conjugate from earlier this year when we practiced simplifying. When you took 5 divided by 2 plus 3i, what did you multiply the top and the bottom by to get the I out of the denominator? The conjugate, which is 2 minus 3i. We multiplied the top and the bottom by 2 minus 3i. Because 2 minus 3i is the conjugate of 2 plus 3i. Okay? So you should have seen that word, or heard that word conjugate before. The imaginary root theorem basically says, if a plus bi is a zero, then a minus bi is also a zero. That's basically the imaginary root theorem. They always come in pairs. So if I told you that 3 plus I was a zero, then what else has to be a zero?
2.
If I told you that 3 plus I was a zero, 3 minus I also has to be a zero. I guarantee if this is a zero, so is that one. If negative 6i was a zero, then positive 6i is a zero. Do you understand that concept? They're always coming in pairs because it's always plus or minus the square root of a negative number. Okay, pretty straightforward. That's the imaginary root theorem. Irrational root theorem is basically the same thing. What's an irrational number?
Not a perfect square.
Not a perfect square. Like square root of 7, square root of 5, square root of 3. Okay, not a perfect square.
No, we're talking about the irrational ones.
So now we're just talking about irrational. If a plus the square root of b is a zero, then a minus the square root of b is also a zero. For the exact same reason. Okay? So irrational roots or irrational zeros will also always come in pairs. The conjugates of one another will always both be zeros. So if 2 minus radical 3 is a zero,
2 plus
then 2 plus radical 3 has to be a zero of the polynomial. If radical 7, if the square root of 7 is a zero, then negative radical 7
is also
a 0. I'll give you an example for that second one here really quick. Let's solve that equation. X squared minus 7 equals 0. Let's solve it. Add 7 to both sides. Square root both sides.
and x equals what?
Plus or minus.
Plus or minus radical 7. X equals positive 7 is a 0. X equals negative radical 7 is a 0. They're always going to come in pairs, those irrational roots, or those irrational solutions. Okay? So, that's the whole irrational root theorem and imaginary root theorem. It's basically they always come in pairs. Pretty straightforward.
So just write for both of them, they both always come in pairs.
With their conjugate. Right? A plus radical b, a minus radical b. A plus bi, a minus bi. Okay?
Always come in pairs.
And then the last thing before I get to your practice problems, okay? I'm going to really simplify this, but the fundamental theorem of algebra is a little bit more in depth than what I'm going to write it, but you're going to get what you need here. The highest power of a polynomial determines the number of zeros. And I've already told you that, yep. Yep. But I don't know if I put it on the board for you, put it in your notes, so it kind of fits along with what we've been. It fits along with these two theorems, and then it'll fit with the practice problems you're going to do. So you kind of got three theorems. You're just taking my word for it that they're true. We're not going to prove them. You can do that if you go be a math major someday. You can prove all these theorems.
I'll get right on that.
I don't know that I can recall the proofs of these. Okay? So, on this next document that we're doing these practice problems, the directions say, state the number of complex zeros, or that's like actually the total number of zeros, okay? So state the total number of zeros, and then it says state the number of possible real and the number of possible imaginary zeros, okay? So, for example, if I was going to do number 1, okay, here's my polynomial. F of x, remember, is just a fancy way of saying y equals, okay? It's nothing to worry about there, okay? What is the degree of this polynomial? 2, because that's the highest power you see, right?
Yeah.
So how many total zeros will this one have? 2. The total number of complex zeros will be 2, because that's the highest power, right?
Yes.
Now they want to know combinations of real and imaginary could you end up with. Okay, we don't need to find the zeros, we just want to know what are the possible answers. So here, let me ask you this. We know there's 2 total zeros, right?
Yeah.
Could both zeros be real numbers?
Yeah.
Yeah. Could both zeros be imaginary numbers?
Yes.
Yeah. Could you have one of each?
No.
No, why not?
It comes in pairs.
Imaginary ones always come in pairs, right? So you can't have just one imaginary zero and one real zero. There's only 2 total. So you either will have 2 imaginary with 0 real, or you will have 0 imaginary with 2 real. Those are your possible combinations. You don't need to find the zeros right now. It just says state how many there are, and state the possible combinations of imaginary and real solutions, or real zeros.
Would you ever just have one or the other?
Okay? What do you mean?
Would you ever just be 2 imaginary and 0 real? And then like that would be it? Or like,
No. No, because unless we go to find our answers, you know, which obviously, when we find our answers, if we were to set this equal to 0, and then it looks like I'd have to use the
But does
quadratic.
that just be all of them though, then 2 imaginary and 0 real?
No, because not if the degree is not 2. Or if, like, the
Yeah, we're
number
going to move
zero.
on to different degrees here and have some different combinations, so I'm going to start with this one.
Well,
Okay.
How do you know?
All right, so any questions just on this right here?
How do you know which one it will be again?
How would I know whether it ends up being this
Yeah.
or this? I'd actually have to go find the zeros.
Okay.
So I'd have to plug in 0 for y, then I'd have to solve that equation. It's not factorable, so I'd have to go use the quadratic formula. And I have to see once, you know, what the number underneath the radical ends up being. If the number underneath the radical is negative, then there's 2 imaginary ones. If the number underneath.
Actually finding out.
We're not actually finding any of the zeros.
That's the answer, right?
That's it.
Okay.
Yep. Okay? That's all you do on this first chunk of problems. I'll do one more for you, just to make sure you have it. We'll do one that's going to have a few more combinations. So let's look at number 3 here. How many total zeros or total roots is this one going to have? 5, because that's my highest power, right? 5 total zeros because of that right there. Okay? Well, what are some possible combinations of real answers or real zeros and imaginary zeros that you could have? Who wants to
5
take?
imaginary and
Can you have 5 imaginary?
4 imaginary.
No. Okay, Natalie, you got the first one. What?
4 imaginary and 1 real.
So you could have 4 imaginary solutions with 1 real. Good. Somebody else, give me a different possibility.
1 imaginary, 4 real.
That's impossible. You can't have an odd number of
2 imaginary, 3 real.
2 imaginary, 3 real.
Oh my god.
Imaginary zeros always come in pairs.
You can do any more than that. I'm really trying. 5 real.
Okay?
You could have 5 real.
Could just have 5 real.
0
So real can come in odd.
Absolutely. Yep.
Imaginary. So
Imaginaries are always in pairs, which means multiples of 2. 2, 4, 6, 8, 10, 12, so on, right?
That's it.
Okay? That's it. Yep. You're done with number 3.
So when if you could get like a really high power, then you could have a lot.
There'll be a lot of combinations. Yep. If I would give you like x to the 18th power, there's a lot of combinations. Yes.
So, like, a good way to think about that is imaginary is like always even.
Imaginary will always be even, yes. Yep. Okay? So again, do you feel like you can answer this first section of problems?
Yeah.
Yes.
Okay? So that's all that you do on 2 through 6. Okay? That's all that you do on 2 through 6. Just what we got done doing. Okay? Now, next section. This is pretty simple here. A polynomial function with rational coefficients. That just means nice coefficients. Okay? Rational numbers, like whole numbers or fractions. Has the following zeros. Find all additional zeros. Okay? So, if negative 5 is a 0, does that mean anything else has to be a 0? No. If I is a 0, then what else has to be a 0? Negative I. Is there anything else?
I have a question. Why isn't it positive 5? Because it's
5 is
real.
not
It's real
irrational.
number.
5 is not imaginary. That only goes for irrational and imaginary roots. Okay? Negative 5 is not an irrational number. Negative 5 is not an imaginary number. Okay? How about number 9? If negative 3 plus radical 5 is a 0, well then,
Negative 3 minus radical 5.
negative 3 minus radical 5 also has to be a 0.
And I.
If negative I is a 0,
I.
then positive I has to be a 0. All you're doing on this section is listing the additional zeros.
What's it? If it's a real number, does that have to be like the opposite of the real? No.
As only for irrational
Alright.
and imaginary.
Got it. So like number 11 would only have like one more.
So negative 1 is 0, good for negative 1. 5 is a 0, good for 5. Negative 2 plus radical 5 is a 0,
Negative 2
so
minus.
negative 2 minus radical 5 is the only additional 0 on that one. Okay? Alright, so that's that chunk.
So wait, wouldn't it be negative 2 negative radical 5?
Negative 2 minus radical 5 would be the additional 0 on that one.
And what would be negative 1?
Nothing.
Negative 5, I mean 5, nothing?
Because real numbers don't have time.
Oh yeah, it's only imaginary.
And